All right. In this webinar, we'll be taking a look at how sheet metal tooling can be made using industrial 3D printers. We'll see what factors you should consider before printing your tooling, what tooling some of our customers are 3D printing and implementing successfully, and our own attempt at printing, stamping, and lessons learned. So with that said, let's jump right in. Before you go about making sheet metal tooling, you need to consider what type of metal and what gauge you'll be forming, as well as the quantity of parts formed with this tooling.
But let's see him take on 2, or 10, or 100, or 1,000!
This also factors into what material and manufacturing technique will be used to make the tooling itself. Now, tool steels are used in large part to manufacture sheet metal stamping dies and bending forms, which require some form of CNC subtractive operation to manufacture. However, with the advent of 3D printing in both thermoplastics and metals, our choices of materials and manufacturing techniques opened up. 3D printers are incredible machines that can solve problems which traditional manufacturing methods like CNC milling and injection molding cannot. Because they build parts layer by layer, a process known technically as additive manufacturing, 3D printers are capable of producing advanced geometries with selectively strengthened features of your choosing, all while remaining hands-free and affordable. This means you can have functional prototypes, tools, robot end effectors, fixtures, you name it, printed overnight for testing, iterating, and implementing the next day. Producing parts at the point of need is how 3D printing reigns king. Now, 3D printing serves two purposes in the sheet metal tooling space. Primarily, it is used to manufacture low-volume tooling, being used to form thinner gauge sheet metal if using thermoplastic composites, moving towards thicker gauges if printing in metals. Secondarily, it is used to prototype the tooling, which can be used to check if the bending die dimensions are correct to fit into the press brake, or verify the geometry of a stamping die component like a punch or a heel block. Markforged states that heel blocks and stripper plates are eligible for 3D printing for metal and composite respectively. That being said, many of the stamping die components, like alignment pins, plates, shoes, fairly uniform components that are quick and easy to machine, and high precision components, should be manufactured traditionally. Now, for many machine shops, hearing the words low volume from a prospect can be disheartening. It is very hard to justify the cost and time to make tooling for such a low return on investment. This is especially true for sheet metal parts. But what if I told you not all low volume jobs have to be so poorly profitable? Don't take my word for it. Let's see how Centerline engineered solutions reversed the stigma and gained a lifelong customer.
The challenges that we run into from a fabrication standpoint and machinery is often a customer will come and they only need one of something, and they usually need it very quickly, and it's difficult to cost effectively make one apparatus, and that's a big challenge that we have. Is I have to have employees that are flexible and a lot of different trade skills in order to turn around one specific part and one specific item. And a lot of times what we'll have to do is we'll have to build fixtures and other apparatus in order to make that one part or assembly, as it may be. And that's some of the big challenges that we face, is going from this individual part to this individual part. And the challenges with the workforce, it's always challenging to find and keep qualified people who know how to run manual machining equipment, CNC machining equipment. I think everyone in fabrication throughout the United States is faced with the same thing. That's also part of where the 3D printing comes in, is that with a 3D printer, it's very precise, and I can utilize some of the things that a manual machinist does with a 3D printer. And that comes in the forms of jigs and other things, so that I don't have to have a machinist work 2 hours to make something that's going to allow us to make something else. I can use a 3D printer straight off of a CAD system to make that.
Well, on this particular part here, we have the indentions, and if we had to get that die made, say out of metal or whatever, we'd have to send off, have it made. It probably costs $2,000 to $3,000. That's where I think they made this one in 5 to 6 hours, and it did exactly what we needed it for. But for specialty dies, this works out real good, and we could use it over and over, and if it does wear out or damaged or whatever, we can make another one and be back up 5 to 6 hours. But if I mess up a die that we send off to have made out of metal, it could be another $2,000 or $3,000. So it saves a lot of money, time, and we're able to design specialty type dies for special parts. On this particular job, it just speeds it up. I mean, because you can spend a lot of time on specialty parts trying to get things to work. And by them being able to do it in the front office, if let's just say I ordered a die and it wasn't right, what are we going to do? We got to send it back. But as far as here, the little problems that we have had, we've been able to correct it.
So, Centerline was able to 3D print a stamping die in about 1 day for $200, what would have cost $1,400 and taken 10 days traditionally. Not to mention, to give added strength only where they needed it, they modeled cavities in the dies and created a print pause in the Eiger slicer at the appropriate layer. This allowed them to insert metal plates to reinforce the printed composite die. Another customer, Lean Machine, found that Markforged's onyx material, when reinforced with carbon fiber, could bend 10-gauge aluminum brackets and up. Let's take a quick look at their experience.
One of the parts we make at Lean Machine is an aluminum wire clip like this. The tooling in general, what we used to use was big heavy steel tooling like this to put in our press brake. So one thing we found we could do with printing was actually print these tools instead. The big thing that we saw with Markforged was it took a big step from a hobby printer to something that you can actually make parts out of. And we saw a few sample parts and then we kind of jumped in with it and haven't looked back. So the first step is that you load the blanks into the trays, which hold 200 parts each. After that, the robot picks the parts out of that tray using an array system and then takes it into the press brake to bend them one at a time. Because of the 3D printing, you have complete control over the profile of your bend. The onyx is actually very good for friction and it doesn't leave any marring on the part at all. So we have a much nicer part with the printed tooling, and it's easier and cheaper to make the tool, so it's kind of a win-win.
One of the biggest real gains that we found with the 3D printer is that if we want to get parts made, we don't have to go and schedule them out in the machine shop. We don't have to order tools. We don't have to make drawings. We can skip all of that and we can just get the parts made on the printer. We come in the next day, the parts are ready, we can start testing with them, and we don't have to go and check that they're right. And being able to have every single feature on a printed part coming out within 2 or 3 thou with Z accuracies of less than 1 thou. I mean, the accuracy stuff is huge. We just keep bending thousands of parts and the tools are not wearing, they're just bending perfect parts. It's like, okay, these guys can pretty much do anything.
Now we've looked at some Markforged customer successes here, but did you know you can also form sheet metal with tooling printed in resin? Formlabs is the preeminent provider of affordable industrial SLA and SLS printers, and the range of materials is astounding, not only in quantity, but also range of mechanical properties. You have pure silicon resins, resins that can withstand short exposures to ignited pure oxygen in rocket engine testing, glass-filled resins that can be used for low-volume injection molds, flame-retardant resins rated at UL94V0, and, of course, your standard modeling resins. Shane, over at Stuff Made Here, made some ingenious sheet metal stamping and bending hybrid tooling. Let's take a brief look at what he's made.
After a bunch of iterations, I finally developed a process for making 3D printed tooling for forming sheet metal parts. The tools themselves are pretty difficult to make geometries, which is well suited to 3D printing, and they only take a few hours to print. The results are getting really quite good, with the parts being what I would consider close to production quality. This is a really great process if there's some parts you want to make that would be difficult to do with normal bending, and you want to make maybe a few hundred or 1,000 of them. So between this and my previous video, hopefully there's enough information that you can replicate these results on whatever part you want to make. Alright, let's see if we can convert that success into another success. This is a more complicated tool. It's inspired by the drip tray on a Breville espresso machine. I think it's a cool part, and I want to see if I can produce something like that because it's a good real world part. And so I have this tool, which basically a bunch of the previous tool arrayed out, and I checked 10 times. There's definitely clearance. So let's see if we can form a grating using this. So it looks like it mostly worked. It has the messed up edge like one of the earlier presses, and I don't know if that is because the press was angled. I had to reseat it, and I also undersized these hole forming tools, so those aren't fully formed. But other than that, it pressed pretty well. It took a little bit of prying to get off the tool, but it wasn't stuck on there like it was before. I would want to maybe optimize this a bit more if I was going to try to make a ton of them. But overall, I think you can do this in one step, although qualitatively, they do seem to come out better when you do it in 2 steps. Of course, I only have one sample here, so this could just be a bad part. But I think this is a good place to end it. You might be wondering why you would print your tools instead of machining them, which should give you a better result. The basic answer is more people have access to 3D printers than they have machining centers. And so if they want a tool, they now have the means to make it, which is awesome. The other advantage is that 3D printing can make a tool that's very complex, very quickly, and very cheaply, which is definitely not the case for normal machining. If you need to only make a few hundred or 1,000 of something, this might be the right process for your application.
Now, with everything that we've seen here, it's time to try our hand at 3D printed sheet metal tooling. More specifically, we plan to stamp our company logo into various types and thicknesses of sheet metal using a Markforged 3D printed stamping die and a drill press vise. After taking some basic measurements from the vise, my coworker James drew it up in SOLIDWORKS and began modeling the stamping die off of this. He took our logo and loaded it into an online site called Convertio that can convert images into DXF files. This greatly reduced the time it would take to create the sketch. After embossing our logo, he used surface offsets to create the relief on the mating side of the die. The M in our logo gave us some fits during this process, so we were limited to a surface offset of about 31 thousandths or less. This meant we needed to aim for sheet metal thicknesses at or below this value. Next, James reinforced the rear faces of each die to prevent them from flexing during compression. Once the design was complete, he exported each die as an STL. It's important to adjust your STL settings to avoid exporting an enormous file. Typically, I aim for a chordal deviation of 0.1 millimeters and an angular deviation of 1 degree. I typically adjust the angular deviation upwards from there if the file size is still over 20 megabytes. I click Save, and it's off to our slicer. In Eiger, Markforged slicing software, I imported the STL files. These parts are a really interesting study on part orientation. If I were to orient this part on this face, with the layer lines building up like so, I actually run the risk of layer delamination. The compressive force on this face of the die could actually cause shearing between the layer lines of the part. This, fortunately, can easily be avoided by adjusting your print orientation. Now for this die, there are two possible options here. However, only one is really the best. If I were to print it on this back face, the issue is how refined the logo will appear. I am at the mercy of the nozzle diameter in this orientation, which is 0.4 millimeters. If I instead print the part, say in this orientation, then I am at the mercy of the layer height, which, if I go into our little settings tab, is 0.1 millimeters. As a result, the logo resolution will be much better. Once I'm satisfied with the print orientation, I double check all settings, and I only adjusted the number of wall layers. Increasing wall layers is a much more effective way at increasing strength than increasing the infill percentage. I reviewed the X-ray view next. And then prepare the parts for printing. Now by this time, we were running out of runway. Thankfully though, we have a Mark II and an X7 in our office. So I sliced one part for the desktop, and one part for industrial. This and the fact that I printed these overnight was a huge time saver. Let's take a look at the printing process. Okay, I know I've been gone from voiceover for a while. Just wanted to mention the parts were removed from their build platforms as we saw. We mounted those into the vise, and we procured a variety of tin, copper, brass, aluminum sheets, all with thicknesses at or below 25 thousandths. And using a pair of tin snips, we cut sections 1¼ inches wide to fit our dies. The first test that we did was using our 25 thousandths thick aluminum sheet. We loaded this in and clamped it.
So we kind of go ahead, situate that.
like make it flush with the top. You ready?
Yeah, go ahead.
I might need to hold the vise a little bit. That ain't working. Is it moving? It's rocking up?
Yeah. I don't think you're gonna be able to get any more.
As you saw, we had some considerable rocking on the floating section of the vise. So we flipped the vise upside down and identified the metal plate needed to be thickened at the rails and elongated. We printed several renditions until we landed with our final design that was printed chock full of fiber. The validation process was greatly aided via the use of Eiger's built-in static FEA simulator. It tests the loading on your 3D printed part based on the fiber routing and print settings you apply. With anchor points and faces set loaded at an estimated 45 pounds total, we can see the maximum deflection and its location, along with the minimum factor of safety. This is one stiff part. However, even after printing this super stiff reinforcement plate, there is too much compressive load just far enough outboard from our fulcrum to still induce this rocking. This was negatively affecting the quality of our stamps, so we needed a more centralized compressive force. So we decided to get another clamp. A really big clamp.
I'm gonna see if I can get it like you know, kind of get some leverage by raising it a little bit. Like that.
Hang on a second. I want to make sure that I'm coming. Okay, now go. 8 weekies.
I know.
The breakfast with the chumps. No bueno. No bueno. Here, just go ahead and let rotate down. That way you don't have to struggle with it. That's pretty closed, isn't it?
Yeah.
Oh, damn.
Oh yeah, that's closing up big time. Nice.
Was it close?
Yeah, for sure. All right, James, I'll let you pull this one out. Sweet.
Since this was our first run using this new setup, we used our thinnest material, 8 thousandths thick tin. Given its success, we decided to try our hand at some 10 thousandths thick brass, our next thinnest material.
It's kicking you now.
Oh yeah, dude. That looks really nice.
Now, at this point, even with our new setup, we could not get crisp quality stamps with material thicker than 10 thousandths. In order to make it work, we needed a higher compressive force than either James or I are capable of producing with manual drive screw vices and clamps. Neither of us having access to a hydraulic or pneumatic press, I tried using my car's scissor jack and the weight of the car to get that much needed high tonnage force. This certainly did help a bit with that 25 thousandths thick aluminum, but we just needed more. And here were our results. You can definitely start to see the logo forming in the thicker materials, so our die is working. As mentioned, we just need a bit more oomph. Oh, and speaking of the die, here are images of the die faces after all of this smashing. Everything survived extremely well with no evidence of damage. The goal is, in a future webinar, to really punish these dies and see what they are capable of. So stay tuned for that. Well, that's all from me. Thanks for joining the webinar, and I guess we'll open the floor to whatever questions y'all have.